In this video, we're going to look at the most sophisticated of the three theories that we have for explaining what electrons are actually doing in molecules. Let's recap a little bit. We'll take our simple H2 molecule and remind ourselves what that looked like in the Lewis theory. In the Lewis theory, we had two valence electrons here. We wrote down a skeleton structure that showed us the two nuclei. And then we counted the valence electrons, 2, and then we connect the structure. There are two electrons inside of a bond, and that bond holds the molecule together. We said that that makes sense before. We said, here's two positively charged nuclei, and here are the little negatively charged electrons wedged between them in that bond. And the whole thing is held together because the positive charges stick to the negative charges. So you've got a wad of negative charge in there that both the positive charges stick to. And it makes sense that that's a bond. Now, we did the valence bond theory picture in the last worksheet. Instead of looking at the particles that were present, like we do in the Lewis theory, we're going to look at the orbitals that are present. So Lewis theory deals with the electrons, counting them. Valence bond theory deals with orbitals. Each of these two hydrogen atoms has a 1s1 configuration in its ground state, so there are two 1s orbitals. They overlap. That overlap is a buildup of negative charge between the two nuclei. And this positively charged nucleus and this positively charged nucleus are attracted to that buildup of negative charge there. And that's how we explain a bond, a valence bond, in the valence bond theory. This third theory looks at the orbitals like waves. Here we're drawing the orbitals in 3 dimensions, but we can also draw a graph that looks like this. Amplitude of the orbital, of the wave, because an orbital is a 3-dimensional wave, versus distance. And let's say the first nucleus is here, and the second nucleus is here. Each of those will have associated with it a 1s orbital, which will look like this. Now, this is showing the amplitude of the wave, which has something to do with how dense the negative charge is. At this nucleus, there's a peak in negative charge. The electron cloud is thickest around the nucleus, and it just sort of tails off exponentially on either side. If we draw in the 1s orbital for the other, it's got a spike right there. Now what happens when these two waves interfere with each other? When two waves interfere, their amplitudes add up. So if we look at this point right here, there's a low amplitude there for the red wave and a high amplitude for the black wave. If we add the amplitude of the red wave on top of where the black wave is, we get a point there. What about this place? Well, both of them have the same amplitude, so about twice up, about that far up, is where the resultant wave is. Now if I keep doing that for a lot of points, I will trace out what the resultant wave looks like. After these two interfere with each other, you're going to get that dotted line wave. Now, that wave is a combined wave. It's called a sigma orbital. It's a molecular orbital. What's a molecular orbital? Well, an atomic orbital is centered on an atom. And a molecular orbital is centered on more than one atom. So it's spread across an entire molecule. And this dotted line is what the sigma orbital looks like. Now here we drew the orbitals in 3 dimensions, and here we drew sort of a graph that showed us where the clouds were thickest. What happens if we draw this sigma orbital in 3 dimensions? What would it look like? Well, say here are your 2 nuclei. It will be a cloud, and notice that there's a buildup of electron density between the 2 nuclei here. It's higher than it was before, and that buildup of electron density is going to hold the molecule together. These 2 nuclei are going to be attracted to that. And if I draw this in 3 dimensions, what I'll get is a cloud. It'll be very thick here, and it'll just kind of fade out as I go out. So where I'm drawing it darker is where there's a big buildup of negative charge. And that's what a sigma orbital would look like. That is what the ground state of the H2 molecule would look like. Now, the interesting thing, one of the most useful things about molecular orbital theory compared to the other two, is that we can work out what the excited state looks like. It is arbitrary whether or not the amplitude of a 1s orbital is positive or negative. In other words, one of these 2 spikes could have been pointing down. If I had this situation where one of the spikes was going up and the other spike was going down, I didn't draw that very well. What would the resultant wave look like in this case? Well, if I add the amplitudes up here, this one's pulling up strong and this one's pulling down just a bit. So when I add those amplitudes, I'm going to get a dot there. Same thing here. This is pulling down and this will be pulling up just a bit, so I'll get a dot there. But what about this point right here? Notice that the top wave is pulling up and the bottom wave is pulling down just about the same amount. So I'm going to have a point where the amplitude balances out to 0 there. It's what we called a node before. And I'm going to get a wave that looks something like this. So it has a node in the middle. That's a point where the electron density is 0. What would the 3-dimensional shape for this one look like? Well, if here are the 2 nuclei, I've got a node in here. This is a place where the electron cloud can't touch. It's going to spike right around either of the nuclei. This is going to look a little bit like a p orbital, except unlike a p orbital, it's spread over more than one nucleus. If it were a p orbital, the nucleus, there'd be only one nucleus, and it'd be right there. But it's spread across 2 nuclei, and the nuclei are in the center of the 2 clouds here. This one is called a sigma star orbital. Now this one is going to be a bonding orbital because there's a buildup of negative charge in between the 2 nuclei. And this one is going to be an anti-bonding orbital because the 2 nuclei have the electron cloud is stripped away between them. They're both positively charged, these nuclei, so they're going to kick against each other and push apart. So this sigma star orbital that I have here is going to be anti-bonding. This one is bonding. And the sigma orbital is always bonding, and the sigma star orbital is always anti-bonding. That star means anti-bonding. What would the energy level diagram look like for this? I have to ask myself which of these 2 waves will have a higher energy. Now, back when we were talking about atomic orbitals, we said that the more nodes you have, that's the more places where you have zero amplitude, the higher the energy. So this sigma star orbital must have a higher energy. We can draw a molecular orbital energy level diagram. This is like our orbital diagram for atomic orbitals, except here we've got molecular orbitals. We've got two of them, sigma and sigma star. So that's our energy level diagram. How would I fill this energy level diagram for H2? Well, there are two valence electrons in here. And just like atomic orbitals, molecular orbitals can only fit 2 electrons. And one of them has to be spin up and one of them has to be spin down. And I start filling the configuration up with the lower energy level. So in H2, I've got 2 valence electrons. 1, 2. That's what the MO diagram for H2 would look like. I've got a pair of electrons in a bonding orbital. Now, that kind of mirrors what the Lewis theory was saying up here. The Lewis theory was saying you've got an electron pair that is bonding things together. So we're kind of seeing why you're getting this 2 property in Lewis theory, why a bond is a pair of electrons, because a pair of electrons fits in the bonding orbital. Now, why can't we have He2? Now, helium also has 2 1s orbitals. Why can we not just overlap them and make a valence bond between the helium? Well, we can't really see why that doesn't work until we come. The valence bond theory says that you can only overlap half-filled orbitals. And one has to be spin up and one has to be spin down. So valence bond theory would prevent you from making a bond here. But why? Let's look at molecular orbital theory. It'll tell us why. We have the same molecular orbital diagram because we're overlapping, or we're building the same 2 molecular orbitals here, a sigma orbital and a sigma star. But how many electrons do we have in helium now? Each helium has 2 electrons, so we have a total of 4. 1, 2. Now that one's filled because 2 is all you can fit into that orbital. 3, 4. Okay, now what does this mean? We have a pair in a bonding orbital, and we have another pair in an anti-bonding orbital. Anti-bonding cancels bonding. We can define something called a bond order like this. The bond order is the number of bonding pairs minus the number of anti-bonding pairs. So for helium here, we have 1 bonding pair and 1 anti-bonding pair. 1 minus 1 is 0. If you have a 0 bond order, that means that this molecule doesn't exist. You don't have a molecule there. Now, what's the bond order for H2? Well, we have 1 bonding pair and 0 anti-bonding pairs. So 1 minus 0 is 1. So the bond order in H2 is 1. And that matches what we predicted with the Lewis theory. There's a single bond there. Molecular orbital theory tells you you have a bond order of 1, which is the same as saying you've got a single bond there. We'll do a few more examples and look at some more things that we can do with these molecular orbital diagrams. And look at molecular orbital diagrams for more complicated systems in the next video.